Hi, my name is Rohan Singhal, and I'm a senior at Centennial High School in Frisco, Texas. I want to say a special thanks to my mentor, Brian Lewis, for guiding and helping me through this journey. My focus for this research project was understanding and predicting gun violence at the county level. Today, we'll be talking about 5 key things. Number one, the introduction, then some context, then the methodology behind this project, then the results, and lastly, the implications and future work. Introduction. My guiding research idea for this project was predictive modeling of gun violence using machine learning, understanding the role of demographic and socioeconomic factors at the county level. Before we dive in, let's clarify some key terms and definitions that will help us understand this topic a little better. Gun violence is acts of violence involving firearms, including homicides, suicides, and mass shootings. Predictive modeling is statistical techniques used to predict future outcomes based on historical data. Lastly, county analysis is the examination of data at the level of counties or similar administrative units. The purpose of this project is to develop proactive strategies and a predictive model for assessing gun violence risk at the county level. Our goals were to uncover the nuanced patterns, correlations, and risk factors associated with gun violence occurrences by using data-driven insights to inform policymaking and intervention efforts. Next is some context. There are some existing challenges of this issue. Nowadays, easy access to firearms, including illegal guns and those obtained through loopholes in gun laws, contributes largely to the prevalence of gun violence in the United States. Building trust between law enforcement agencies and the communities they serve is crucial for effective crime prevention and intervention efforts. Socioeconomic factors such as poverty, unemployment, and income inequality are closely linked to higher rates of gun violence, which highlights the need for comprehensive social and economic policies. Despite widespread public support for measures like universal background checks and assault weapons bans, legislative action on gun control remains challenging due to political polarization and the influence of special interest groups. But why does this matter? Well, gun violence is a significant public health issue, causing thousands of deaths and injuries each year and imposing substantial economic and social costs on communities. Preventing gun violence enhances community safety and fosters a sense of security among residents, contributing to the overall well-being and quality of life. Additionally, access to safe environments free from gun violence is a fundamental human right, which is essential for humans to exercise their rights to life, liberty, and security. Gun violence imposes substantial economic costs on society, including medical expenses, lost productivity, and expenses related to law enforcement and criminal justice interventions. Now moving on to some statistics and trends. According to the Centers for Disease Control and Prevention, also known as the CDC, approximately 74% of all homicides in the United States involve firearms. Furthermore, as reported by the American Foundation for Suicide Prevention, firearms are used in about 50% of all suicide deaths in the United States, making it the most common method of suicide. And lastly, as of 2021, approximately 32% of American adults personally own a gun, according to a survey conducted by the Pew Research Center. Next, we have some methodologies. For data collection, we source comprehensive data sets from reputable sources such as the United States Census Bureau, the Centers for Disease Control and Prevention, and the Federal Bureau of Investigation, or the FBI. These data sets encompass a wide range of variables, including crime rates, socioeconomic indicators, and demographic data, providing a robust foundation for our analysis. During the exploratory data analysis phase, we encountered raw, unformatted datasets with inconsistencies and missing values. To address this, we leveraged Python programming along with the Pandas library for data cleaning and pre-processing. We conducted data normalization and aggregation at the county level, ensuring data integrity and consistency. An essential component of the analysis involved integrating geographic information with the datasets. The Google Geocoding API and Google Maps geolocation services were used to geocode the location information provided in the datasets and derive latitude and longitude coordinates. These coordinates were then employed to query the API, which yielded the FIPS, also known as the Federal Information Processing Standards code, which encapsulates the geographic identifier at the county level. This enabled the linkage of gun violence incidents to specific counties, which facilitated a thorough spatial analysis. To extract temporal insights, the data underwent a conversion from wide to long format. This transformation allowed us to extract the year from variables related to unemployment and poverty rates. Subsequently, the data was transformed back to its original format. This approach provided a granular temporal dimension, enabling a closer examination of trends and patterns over time. In our analysis, we employed logistic regression and random forest algorithms for predictive modeling of gun violence risk. Logistic regression allowed us to model the probability of a shooting occurrence based on various predictor variables. Additionally, we utilized tenfold cross-validation to assess the performance and generalization of our model across diverse datasets. This technique involved splitting the dataset into 10 subsets and then training the model on 9 subsets and evaluating its performance on the remaining subset. The random forest, on the other hand, provided a more robust ensemble learning approach, considering multiple decision trees to enhance the predictive accuracy. To efficiently do all this, we utilize Python along with essential libraries such as pandas for data manipulation and scikit-learn for machine learning algorithms. Python's versatility and rich ecosystem of libraries enabled us to streamline the data analysis process, from data pre-processing to model implementation, facilitating efficient and effective analysis. Here is a visual representation of our decision tree, which helps us understand how our predictive model works. We use decision trees to help visualize the model's decision logic. Although the tree shown here is one example out of many, it illustrates how the model classifies counties based on various factors. Each box in the tree signifies the decision point where data is categorized as either shooting or no shooting, which is coded as 0 or 1, respectively. While this decision tree is simplified, it accurately captures how the model classifies counties. Now let's talk about the results of this project. The random forest model's performance was evaluated using tenfold cross-validation. Across the folds, the accuracy was consistently high, ranging from 0.91 to 0.95, and the average accuracy across the 10 folds was 0.93, as you can see on the left. These accuracy scores highlight the model's ability to correctly predict gun violence risk on a scale of 1. The model's effectiveness was further measured using the weighted F1 score, which accounts for both precision and recall. The F1 weighted scores range from 0.9 to 0.95 across the folds, and the average weighted F1 score across the 10 folds was 0.92. This indicates the model's balanced performance in predicting both positive and negative instances. Additionally, the model's performance was assessed using the macro F1 score, which considers the balance between precision and recall for each class. The F1 macro scores range from 0.55 to 0.81 across the folds, with an average of 0.67. These results demonstrate the model's ability to generalize well to diverse data and maintain consistent performance across different subsets. We used a feature importance chart, which visually represents the contribution of different input features, also known as independent variables or predictors, in determining the output or target variable. It ranks the features based on their importance or influence on the model's predictions. These are valuable for understanding which variables have the most predictive power and can help identify key factors driving the model. In our case, poverty-related variables were the most significant. The analysis revealed that the total number of people in poverty was the most influential factor in determining shootings at the county level. Moreover, the analysis of the feature importance chart on the right revealed key factors influencing gun violence risk. Notably, variables related to poverty, such as the 90% confidence interval upper bound for total poverty, which is the topmost feature, exhibited the most substantial impact. Counties with higher upper bounds of total poverty were more likely to experience gun violence incidents. This observation indicates that the sheer size of a county's population in poverty plays a crucial role in influencing the occurrence of shootings. Moving on to the implications and future work. Policymakers can make informed decisions regarding resource allocation, legislative measures, and community-based initiatives aimed at preventing gun violence. Law enforcement agencies can leverage the predictive models developed in this research to enhance proactive policing strategies. By identifying high-risk areas and vulnerable populations, law enforcement can allocate resources more effectively, deploy targeted interventions, and improve response times to potential threats, ultimately contributing to public safety and crime prevention. Engaging communities in discussions and initiatives related to gun violence prevention is crucial for fostering collaboration and promoting collective action. By sharing the findings of this research with community leaders, organizations, and residents, we can raise awareness and empower communities to take action. Future research could explore longitudinal data spanning multiple years to analyze trends and patterns in gun violence over time, as the research used in this project only analyzed data in 2021. Further investigation into advanced machine learning techniques such as ensemble methods, deep learning algorithms, and spatial temporal modeling could enhance the predictive accuracy and robustness of the models. Expanding the scope of data sources to include additional variables and indicators from diverse sources such as healthcare records, social media data, and community surveys could enrich the analysis and provide a more comprehensive understanding of the factors underlying gun violence. By integrating a wider range of data sources, researchers can gain deeper insights into the complex dynamics of gun violence and inform more holistic prevention strategies. In conclusion, total poverty is the most influential factor in determining mass shootings at the county level. This research is significant because it addresses the pressing issue of gun violence and provides insights that can inform evidence-based policies and interventions. By leveraging advanced predictive modeling techniques, the research contributes to the ongoing discourse aimed at preventing and mitigating gun violence at the county level. So, let's work together to combat gun violence and make a meaningful difference. Together, we can build a brighter and safer future for all. Thank you.